Hello, everyone, and thank you for joining us today. My name is Mary Monson, Senior Manager for Technology Partnerships and Business Development at Sandia National Laboratories. I am thrilled to kick off this Department of Energy National Lab Discovery Series webinar. Today, we'll be exploring materials data-driven design, or MAD³, as you saw in the video, developed at Sandia. In addition to hosting this event, the Sandia team will also share insights on partnerships opportunities. We are also privileged to have Hojun Lim and David Montes de Oca Sapayan with us, who are the developers. And they will share their expert perspectives on the technology. And we also have, in addition, Debbie Hudgens, a Sandia licensing executive. Before we proceed, I just want to remind you that your microphones will be muted throughout this presentation. If you have any questions, please just type them in the Q&A tool that you'll see at the top of your screen. Or it could be at the bottom of your screen, depending on the system that you're using. And we'll address your questions during the Q&A session at the end of the webinar. So without further ado, let's dive into the fascinating world of MAD³.
All right. Thank you, Mary, for the wonderful introduction. It is my great pleasure to present our work today. My name is Hojun Lim, and alongside my colleague David, we'll be introducing our software, MAD³, which stands for, again, Materials Data-Driven Design. So this software is specifically designed to accelerate material simulation, particularly in characterizing materials directional strength. So here are our quick bios. Both David and I are staff scientists at Sandia National Labs, working in the computational materials group in Albuquerque, New Mexico. My background is in material science with a focus on metal plasticity, while David brings expertise in machine learning and AI as applied to material science. So together, we teamed out a little over 5 years to develop this capability. Okay. All right, so as a material scientist, I want to start emphasizing the importance of internal structure of a material, or the microstructure, which plays a significant role in determining its properties. So metals are typically made up of these small micron-sized grains or crystals, and collective behaviors of these single crystals determine the bulk property of polycrystalline metals that we see every day. So the property of interest in this work is materials' directional mechanical strengths, commonly referred to as plastic anisotropy. So, for example, if you pull or apply a force to a material in different directions, like transverse or 45 or rolling directions, you would see varying response. And this property is very important in structural applications, as it directly influences strengths and failure characteristics and formability in metal applications. So in industries such as automotive manufacturing, this ability to form parts from sheet metals heavily relies on understanding these properties. However, accurately achieving this property is not a trivial task. The manufacturing industry lacks effective solutions, and there's a strong need to enhance efficiency and accuracy in characterizing plastic anisotropy in different industry sectors as well. So the market has a strong demand for acquiring these material properties, but there are some challenges and problems. So characterizing anisotropy can take from days to weeks, and typically requires specialized equipment and technical expertise. So naturally, this leads to significant resource allocations and making it very costly. Some manufacturers spend millions each year to characterize this behavior. Also, this leads to some operational shortcomings as industries react to issues rather than proactively forecasting them. So there is also value of depth in R&D data, where R&D data is difficult to understand and it's difficult to implement findings into the manufacturing side. And lastly, there's a growing concerns about the carbon footprint as associated with many different physical experiments. So our solution to this problem is to develop a tool that leverages the power of machine learning trained from huge high-fidelity computational data. And in the next couple of slides, I'll discuss more details about the software that is based on the fundamental science, but aimed at solving this engineering challenge. All right, so what is MAD³? It is a machine learning-based solution, a software application that uses microstructural data to predict directional strengths in metals. So we trained this model from huge data set, more than 70,000 high fidelity, expensive simulations. And we have used this deep learning, machine learning algorithm, more specifically it's called variational Bayesian inference neural network model. And this algorithm was packaged into an easy to use graphical user interface or GUI. So one of our top priorities was to make it accessible to anyone, regardless of their expertise in computer science or material science or machine learning. So now it is on a web-based software, so users don't have to worry about the installation or compatibility issues with different operating systems. Here's a little bit more detail about the software. The input for the software is the material's microstructure data, which you can typically obtain from X-rays or electron backscatter data from electron microscopes. And that has information about material's crystallographic texture data of the material. So once the input data is added to the MAD³, the software processes the data, and in a few seconds, it provides this directional strengths or the anisotropy or these thinning ratios, what we usually call like R values, as well as material data or parameters for different yield models, which you can directly incorporate in any like continuum scale simulation software. So again, the MAD³ has a big advantage in speed versus accuracy, if you see on that top right corner. And it uses pre-trained machine learning tool, so that eliminates the need for expensive experiments or simulations. So it is easy to operate, it is fast and cost effective. So now I will pass my mic to David, and he will demonstrate the MAD³ software and share our success stories and some market opportunities and how it can help different customer segments. So David?
Absolutely. Thank you, Hojun. Thank you, Hojun, for walking us through how this technology was developed and its potential implementations. As Hojun was mentioning, we packaged this software solution into an easy-to-use GUI that is deployed via the web. So you just need to go to this website, right? And you can obtain a username and a password, right? And once you get that password, you can log in. Once you log in, we strived to make it extremely easy to use. So we went with this minimalistic design, and you come to this home page, right, where the big upload data button is straight in front of you. So once you click it, right, you can essentially upload your data. The input to this software as of right now is the texture of the material, which, as Hojun mentioned, can be obtained using X-ray diffraction or electron backscattering. You input a little bit more of the metadata into the terms of how the data was collected, right? And then you pick which of the complex yield models you want to calibrate, right? At this point, I want to mention that without MAD³, if you want to calibrate any of those models, you would either need to run an expensive high fidelity simulations, which requires for you to have high performance computing, or perform experiments, which means that you will need to have a lab and specialized subject matter experts to run this. With MAD³ you just simply click run MAD³, right? And in a couple of seconds, right, you get taken back to the homepage and the results now change from color to green. When you click on the results, that means that they become available. You are greeted with this page right here that shows you how ordered or disordered your underlying structure is from the data that you got. It also provides you with your normalized yield stresses. These are the directional strength that Hojun mentioned, and essentially you see that as the angle changes, right, those will change depending on the texture of your material. You also get information about the thinning ratios or R values, right? And you also get information about the yield surface. Most importantly, after all this, right, you also get information about the calibrated parameters, right? You see, on this case, we selected Hills 48, which is one of the most commonly used, right? And we obtained those 6 values essentially with the click of a button, right, using a standard laptop on a on an easy to use GUI that is deployed via the web, so you don't need to worry about installation, right? So naturally, right, as you can see, right, MAD³ provides the capability to calibrate complex deformation models. That this capability was only previously available to a handful of companies and research labs, right? However, with this capability, we now are able to do it, right? And this naturally presents a significant opportunity and opens new implementations and applications for this. We're highlighting at this point a couple of the successes that we've had, right? And on the top left, we see an example of characterizing plastic anisotropy, which in other words means characterizing the strength, the directional dependence of strength of a material. I want you to focus on the black squares, right? So as you can see, this material has significant load dependence behavior because we see from 0 to 90, it changes significantly, right? If you didn't have MAD³, you would need to perform these physical experiments, right? And as I mentioned before, you would need to have a lab, subject matter experts, right? But with MAD³, right, focus now on the green squares, you're able to obtain a similar trend, right? But you were able to obtain it in less than a minute using a GUI. For a second success story that we want to highlight, right, is we were able to successfully perform a cup drawing simulation, right? In this simulation, we used a complex model called Yield 2000 that requires 18 parameters, right? If you do not have MAD³, you would need to calibrate those 18 parameters doing experiments or running high fidelity simulations on a high performance computing environment. Calibrate those parameters using the high fidelity simulations took 10 hours on a high performance computing environment, but with MAD³, we're able to obtain them again in less than a minute. And as you can see, the resultant simulations, right, performed with the high fidelity calibrated parameters versus the MAD³ calibrated parameters are essentially indistinguishable. Finally, this is one of the most exciting ones and one of our newest applications, right? It's applied to additively manufactured steel. Additively manufactured steel has bigger of these grains, right? So it has more intense directional dependency, right? And we need to account for it, right? Especially if we want to see how this material will behave in extreme environments under high deformation rate and at high temperatures. But before, we were not able to account for this directional dependency because we would need to calibrate those models, right? Naturally, right, to calibrate those models with experiments or simulations, as I've mentioned before, right, takes significant amount of time. But now with MAD³, we're actually now capable to do that. We put 2 QR codes of the two example papers where we go into this into detail. So naturally, right, the capability to calibrate these complex models, right, and to do it efficiently and effectively presents a unique market opportunity, right? We went the extra mile and we decided to validate this market opportunity by performing over 75 different customer discovery interviews and talking to over 120 different people, right, to see how essentially the capability to address this, right, to be capable of characterizing the load-dependent behavior of materials in seconds rather than weeks or days, right? How could it benefit, right? Naturally, right, this presents um, a significant market opportunity, right? And the invaluable insights, if we could change slides, please, sorry. The invaluable insights obtained with this customer discovery interviews enable to identify a large number of customer segments with MAD³ where MAD³ can have significant impact. For example, we discovered that in academia and research lab, MAD³ can be successfully used to perform material discovery and identify the best next alloy in an easy and in an effective and efficient way. We also discovered that for aerospace and for automotive companies, right, MAD³ can be used for material selection and component simulations, right? Now, when performing a forming or stamping simulations, these manufacturers can actually use the material that is being stamped, so they can actually account for the true directional dependent behavior rather than rely on parameters that were calibrated many years ago and do not reflect the material being stamped. Also, we were able to, for metal manufacturers, right, this provides them with a more in-depth property and material characterization, as well as process control, because now their technical data sheet of the material can include information about these complex yield models. And finally, right, for software companies, software simulation companies, this allows them to use and develop more complex material models, right, since now the users are actually able to use and to use these materials is now they're able to calibrate for this material. So, as you can imagine, right, the successful product that is MAD³ was not developed overnight. As a matter of fact, it has been a multi-year effort that started all the way back in 2021 and 2018, sorry, with funding from Advanced Simulation and Computing that helped us perform the fundamental research, right, that allowed us to build this efficient connection between the underlying structure and the resultant property. However, what is unique about this research code, and I would not call it research code, about this software solution, right, is that we actually developed it. We went out of the lab and we interviewed people that we think that could benefit from this technology, right? And we were able to successfully do that through the Energy I-Core program, right? So this allowed us to develop this as a technology pull rather than a technology push, because we were developing technology that addressed the main pain points that companies and manufacturers and our envisioned users do it. So we performed that in 2021. We protected with the intellectual property with a copyright assertion, right? And the invaluable insights that we obtained from the I-Core experience and talking to all these different potential customers enabled us to secure funding from the Sandia Technology Maturation Fund, which allowed us to essentially go from this research code to a full-fledged market solution, right? And in 2023, this became available. And the significant impact, right? And just in the way this was developed, that it tackled problems that are faced currently by industry, enabled us to be recognized as one of the top 100 most innovative inventions of 2023 through an R&D 100 award, right? And this commercialization journey is far from over, right? In 2025, we're still continue to work with I-Core. We put in a proposal to expand our prototype, so now that we can provide a full-fledged solution where we do not need, because as of right now, you need to input the underlying texture of the material. We are working on developing a prototype where you can just provide a sample and then MAD³ takes the complete takes care of the complete task, right? So we're combining software and hardware. And in 2026, thanks to this opportunity from the National Labs Discovery Series, we're looking for partnerships, right? And we're looking for opportunities to apply this technology. And with that being said, at this moment, I would like to pass it on to Debbie Hudgens. She would explain about the different opportunities and ways in which you can collaborate with us. Thank you.
Thank you, David. We do partner with partner through various partnering mechanisms. We partner with all types of organizations, large entities, startups, universities, and government agencies. We can partner through various mechanisms such as collaborations. These can be CRADA, Collaborative Research and Development Agreements, or SPPs, Strategic Partnership Programs. The CRADAs are longer and more collaborative in nature, whereas the SPP is shorter and it's more directed work for Sandia to carry out. Under the CRADA, the partner gets free access to background IP. They also have an opportunity to negotiate up to an exclusive license for any subject IP. And this is typically, we partner with one or more non-federal entities, and those partnerships can be at least a year, and we've even had some for decades, actually. The SPP, on the other hand, is much shorter, 16 to 18 months typically. And as I mentioned, these are more focused scopes of work for Sandia to carry out. We also have licensing, and we have a variety of options there as well. We have a test and evaluation license, which is a very low-cost research license, as well as license options. These are research licenses that also provide an opportunity to gain a commercial license before the end of the term, as well as commercial licenses, which can be non-exclusive or have some level of exclusivity. Each provides a different scope of rights to help de-risk the investment for the partner, and we have very flexible licensing terms. And we work with the other party on developing these. We really strive to achieve an agreement that's beneficial for both groups because our primary interest is really to get these technologies out of the lab. Another pathway is the user facility. These can be made accessible to companies and other organizations to access equipment and lab facilities. For example, we have the Center for Integrated Nanotechnologies, and we have many companies and organizations that currently utilize this space under a fee-based service agreement. Another partnering pathway is through the Small Business Technical Assistance. There are two programs in particular, the NMSBA and Trigger programs that support startups that are incorporated in the state of New Mexico. This can lead to vouchers, research vouchers of $20,000 up to $150,000 for work to be conducted at Sandia National Labs or Los Alamos National Labs. All of these allow access to our technical expertise and connection to the communities of innovators. We are seeking partnerships for MAD³, and as well as a number of other opportunities. Please do visit our website at ip.sandia.gov for more information, where you can find 1,800 pieces of IP for viewing. Thank you so much for your time. All right. I think now we can actually segue to Q&A. So we've already received some great questions, and we'll start addressing them shortly. Please continue to submit your questions using the Q&A tool as we proceed. We aim to cover as many as possible during our session today. Okay, so coming to our first question, will the data set be made open source or is it proprietary?
Thank you. I can take that. The data set is proprietary, as I mentioned before. One of the things that we discovered through this different interviews that we did is that this is a significant market pain point. So that is one of the biggest part of the intellectual properties, and essentially it's a moat that enables us to do what no one else can do before. As Hojun mentioned, we performed over 70,000 simulations, which means that we were one of the handful of researchers available to do this. So naturally, this comes part of the intellectual property that we're protecting. However, just to add into that, as Debbie was mentioning, through CRADA, there's different access to all these different intellectual properties. So that's the purpose of this seminar, is to learn more about the different opportunities and how we can collaborate.
Excellent. Another question is your machine learning model a feed-forward neural network? How does this model handle discontinuities?
I'm
I'm
just
sorry, discontinuities in rotation representation.
definitely. Oh, okay. I think just to provide a little bit more of detail on that, and Hojun, feel free to step in if you want. But one of the critical things that we did is that we're representing the internal structure of the materials for these rotations, right, using generalized spherical harmonics. So generalized spherical harmonics, and if I get too much into details, just I apologize, but it's a way in which you can represent these crystal orientations in a Fourier representation that accounts for it, right? And that enables us to account for these discontinuities. So it's not the model itself, it's the representation we use in which we train the model. And any of more of the technical details, maybe Hojun, you could go back to the success stories slide where there's a QR code for the papers. All of those details are provided in those two papers so that people, yes, there.
Excellent. We have another question. How do you verify, validate, and quantify uncertainty for these machine learning models? Have you compared these results with traditional finite element method, FEM, and advanced material models like Hill 48, Barlotta, to stimulate anisotropy?
Definitely. So I'll answer these questions separately, and I'll let also Hojun provide a little bit more of input on that one. So in the second paper over there, the one that is Park et al., right? That one provides more detail about experimental comparison, right? I'll let Hojun tackle that. But in terms of the uncertainty, right, we're using a variational Bayesian inference neural network, which is a neural network that enables one to provide not only a single prediction, but rather a distribution, right? So this enables for the model to tell us when it's certain and when it's most uncertain. And Hojun, do you want to tackle the one about comparing to existing high fidelity models?
Sure, yeah. So our model was trained from crystal plasticity simulations. So it does provide, so the MAD³ provides anisotropy coefficients for Hill 48, Yield 2000, Bala 2000, and 2004 models as well. So we have, again, as David mentioned, in those papers from Park, you'll see how it compares with some of the parameters from the experimental characterization and from the crystal plasticity and also from the MAD³. You'll see some of that result in that paper. And it agrees relatively, I mean, pretty well looking at those R values and directional yield strengths. I hope that answered your question.
All right, another question. Can MAD³ be applied to ceramic materials such as silicon carbide or silicon nitride?
So maybe I can take that question. So this model was trained for metals only, for FCC and BCC metal alloys. We have validated with experimental data from few different aluminum alloys and few steels, but we haven't really tackled on non-metallic materials.
However, if I might add to that, and in the spirit of these partnerships, right, the protocol essentially would remain similar to what Hojun mentioned. That means that if we have simulation data for ceramics, right, we can similarly build a database for for such for such materials and establish a similar surrogate deep learning based model for it, right? So that could be something in which we could partner, right? However, the critical part would be to have accurate and validated finite element simulation software for ceramics. because as Hojun mentioned, this was calibrated for metals only.
And is MAD³ capable of elevated temperature simulations?
As we mentioned before, so these focus solely on the initial characterization of load-dependent behavior, right? So that's what calibrates them. That's what provides the calibration for the models. However, once you have the calibrated parameters, right, you can actually use those parameters to run simulations at higher temperature. One of those examples is the one that is currently on the slide on the right. In those ones, we used MAD³ to calibrate the yield models for these additively manufactured microstructures, and then we ran simulations of essentially shock simulations at high temperature and high pressure, right, for these materials. So the model itself just it's usable for calibrating the load dependent behavior of the materials. The resultant calibrated parameters can then be used for other applications.
And can I just add that our model, we have used room temperature with a quasi-static rate. So the temperature and rate effect on anisotropy was not really trained in the current version of the model, but we have questions about how much the rate and temperature affects the plastic anisotropy. So that will be definitely a future work for us as well.
Does the training set fully synthetic? You mentioned 70,000 simulated samples, but are there experimental data as well?
Absolutely. Hojun, do you want to tackle this one and I can complement?
Yes, so all the training data was generated from the crystal plasticity, so all computational data. We haven't not used experimental data to train the model, but we have used few experimental data, limited data that we had for the validation of our model. So it was not used for the training.
However, just to complement, piggyback on what Hojun said, right? The high fidelity simulations were thoroughly validated and we're using essentially a highly accurate model, right? And we have used experiments to validate this. And one of the examples is on this slide on the top left, where essentially you see the black squares are experiments, right? And the green squares are the MAD³ results, right? So.
Excellent. Another question for you. Can MAD³ handle multi-phase, having other than single FCC or BCC phase?
Absolutely. Hojun?
Yeah, that's great point. Great question. So, and that's definitely where we are heading towards. So currently we can only do the single phase material, but we just started to create some data set for the multi-phase materials, and yeah, that's definitely something we are interested in.
And just again to add a little bit more into the things that Debbie mentioned, right? Those are all great areas for collaboration with Sandia, right? And there could be many different ways in which we can leverage the existing. We could use MAD³ as a stepping stone to address all these different questions, right? And all these really interesting research and manufacturing issues.
We are getting a couple of questions about application. I think this is something that you had addressed, but maybe you can expound upon it a little bit. If it is beyond the automotive sector, what specific applications you both kind of see going forward?
Yes, absolutely, right. One As we mentioned before, maybe one of the things where we focused was on automotive, and we were able to identify this through the I-Core program, right? But as we mentioned there, and we have on this slide that Hojun just posted, we identified many different potential customer segments, right? For example, I can expand upon a little bit on the metal manufacturer, right? You have these metal manufacturers as of right now, they do provide with the material they supply information about the yield strength, right? Or information about the thinning ratios, but they only provide them in a single direction, right? Naturally, and as Hojun mentioned, in material science, the internal structure of the material plays a significant role, right? So even if you have nominally chemically the same aluminum roll or steel roll, right? The microstructure will play a big role, and you can have different directionality dependence, right? So with MAD³, right, metal manufacturers would be able to provide more in-depth information about the material they're providing. And this is just an example, right, about the directional dependent strength on not only on the rolling direction, but as well maybe the transfer direction, or many more, right? As the slides we've showed before from 0 to 90 degrees, right? That is an example, right, where it can be applied to other customer segments, right? In the material simulation software, expanding a little bit more on that, is now users can actually use more complex models, right? Like the Yield 2000 or Barla, those that have higher number of parameters, right? Because before they would have to use either calibrated parameters from other materials, right? Or from a handbook or that were calibrated years ago, right? And now you can actually use the parameters that were calibrated to the material that you're going to be stamping, and along on many other examples that we can find. So, and I do want to mention that this is not by all means an all-encompassing list. Those were the ones that we were able to identify through the customer discovery effort that we did.
There, David and Hojin, there's this specific question about capabilities for nanoparticles for energy storage similar to COMSOL. Is that something that's been considered?
Hojun, do you want to take a stab at that one?
Yeah. So this software is for anisotropy prediction, and it doesn't have any capability for nanoparticles for energy storage. So no, it does not have that capability currently.
Okay. And another question for both of you is, are there any materials that MAD³ cannot process?
Right. So again, this model was trained for FCC and BCC metals, and so anything outside that, multi-phase, or if you had some let's say HCP material, for example, it is not in the current version of the MAD³. Or if it's non-metallic materials, it probably won't work.
Okay. There was a question that we received, if the model does include anything about grain size and shape.
Yes. So one of our assumption was that crystallographic texture dominates the plastic anisotropy effect. So we did some tests with the varying grain sizes and shapes, but the current version of the MAD³ does not consider grain shapes and sizes. So a little you can find a little more detail in that, in our papers. So you'll see how much that affected anisotropy behavior. But we thought it's not the dominant factor is the crystallographic orientation or the texture.
Excellent. We are just getting so many questions, it's hard to keep up with these. Is MAD³ able to simulate highly porous materials?
So again, for example, maybe to just provide a little bit more context of this, Hojun, could you go to the cup drawing simulation slide? Yes, perfect. So what MAD³ would enable, right, and to echo what Hojun said, if you have a material that is FCC face center cubic or BCC body center cubic, right, you will be able to run MAD³ and calibrate the yield models, right? Currently, we have 3 or 4. I do not remember from the top of my head, right? And after that, you can run a simulation of a finite element simulation. So, for example, in this case of the really specific porous one, right? if the material is FCC or BCC and you have a yield model that is within MAD³, then you would be able to run a simulation of that porous material, of how it behaves, right? Because MAD³ will enable you to calibrate the parameters for the yield model for that material. Anything that you might want to add on that, Hojun?
No, other than that, we haven't trained our model with some porosity or some defect density, varying defect densities. So it probably won't, we can incorporate those information in our current model. But, if that's something of an interest, we could create some data set and retrain the model to incorporate those porosity or any other defects in material. That might be a possibility, yeah.
Okay, another application question. Is the software capable of predicting chemical reactions from specific metals used as catalyst?
No, it does not do any chemical reaction predictions, or we don't consider those in our current model.
Excellent. There are lots of questions, and we should hopefully be able to get to many of you, if not today, but after the call, hopefully. There was a question about partnerships and having a green card status. That having a green card status or U.S. citizenship, you can get access to the different licenses that I mentioned, even the research license. I think that's what the question was directed to, but any of them, you would be able to, to negotiate license. We do have some sensitivities for foreign nationals of specific countries. And sometimes we can, depending on the technology, sometimes we're able to get special approvals. But by and large, if you are a green card holder, a U.S. citizen, we are, more than happy to work with you and your organization. Okay, well, I think that we are coming to a close. I will maybe just take one or two more technical questions. There is a question if the training set used 2D models or fully 3D crystal plasticity.
Hojun, do you want to tackle that?
Yes, it was a full 3D crystal plasticity models for our training data.
Okay. And I think we'll just take one more here. Are you able to simulate corrosion of the materials in different environments?
No, the current model, we don't have any information about corrosion or the prediction of those properties. We just provide anisotropic strength predictions from this version.
Okay. Excellent. So lots and lots of questions have come in for you, Hojun and David. Did you have any kind of last comments? Otherwise, we'll be wrapping up shortly.
So, so the current version of the MAD³ is hosted on Sandia's restrictive network SRN, but we do have external facing version available. So if you're interested, we could provide the link or the account to access it and do some trials and etc. So please contact us if you're interested. I'll put our emails and contact information here. So please feel free to ask us any questions or anything, any future collaboration. We really wanted to have more discussion and be happy to chat.
Absolutely, and just to echo what Hojun was saying, this is we have done some great work into developing MAD³, but we do recognize that this is not the end all and be all solution, right? We see it as a stepping stone. So echoing what Hojun said, we are really interested in collaborations, in partnerships, right? As Debbie mentioned, there are many multiple opportunities for us to collaborate, right? MAD³ is available for licensing, as she was saying, right? So if you're interested, we do have that external facing version that Hojun was saying, so that we could license and partner with you. So with that, I would just like to thank you all for your time. Thank you for your interest and all your questions. As David mentioned, we'll try to get to all of them, right? And we look forward to learning more about, and we are super excited for all the interest that this has garnered. So thank you for your time.
Yes, thank you, Hojin and David, as well as all of you for attending today. That wraps up our Q&A session. If we couldn't get to your question, don't worry, we will follow up. We did have lots that came in, and we will follow up with you by email within the next week. Should you have further questions, please feel free to send them to us by email, which you can see at the bottom of your screen. Thank you once again for your participation in today's webinar. Your engagement and interest are greatly appreciated, and we look forward to welcome you to future sessions. Thank you so much.